Hello friends, here in this video we will see a derivation of flexural formula for pure bending, and for that purpose here I will draw the diagram that considering a beam which is simply supported at its two ends. Here we have the horizontal beam which is supported, I will say these are ends A and B, or I can say ends A dash and B dash. Now when we are deriving the flexural formula, it is the bending formula, and for that here I will assume on this beam there is a point load W acting at the center. So the distance is L by 2 from A and L by 2 from B. So now under the action of this load W, the beam A dash B dash, it is going to bend, and the nature of bending will be in this way. So here this arc which I am getting, it is the bending curve of a beam. So now we have to derive the formula which is called as the flexural formula, and flexural here it means bending. We are going to derive the bending formula here for the case which I have considered by taking an example of point load. But even if we apply the uniformly distributed load, then also the beam will be bending in this manner. Now what I will do, I will say that consider the beam section before bending as shown below. Now here I will consider the section of this beam before bending. So when the beam is not bending, it means it is completely straight, then the diagram will be in this manner. Now after this, here I am considering a portion of a beam. On this I will take two sections. One is section AB and the other is section CD. Now here I have taken a part of that beam, and in that part I am taking two vertical sections. Next here I am drawing the center line for this beam. Now on this center line here I will mark a layer joining AB and CD, and this layer is called as EF, and here the central axis which is passing through the beam, it is also called as neutral axis, denoted by N suffix A. So I have taken the section of this beam which is before bending. Now after this, here I can say that the length of this beam which I am considering, that is between section AB and section CD, the length of the beam I am considering is dx. Next after this, here I will say that consider another layer GH at a distance small y from neutral axis NA. Now here from this neutral axis I am going to consider another layer which is layer GH and its distance from the neutral axis is y. Now, what I have done up till here is that I have considered the bending of a beam and then taken a section of the beam which is before bending, and in that I have taken two vertical sections, that is AB and CD. Between them the length of the beam is dx, and I have taken the center of the beam which indicates the neutral axis, and on that I have taken the layer which is called as layer EF, also called as the neutral layer. Next, from this EF at a distance small y, I have taken another layer which is called as GH. Now this was considering before bending. Now after bending, what happens is, I'll say that considering the section of the beam after bending. Now after bending, how it will look like, first I'll draw the diagram for that. Now, when the beam is subjected to loading as shown in the diagram, this beam section which was straight before loading, now when the load is acting, that beam will bend in this way. So what will happen is, these points A, B, C, D all would be shifted. So here I'll mark those points. So here is for A, when it gets shifted, I'll mark A dash, B as B dash, then C dash and D dash, joining them up to the center where they will intersect. There we will get the center. Now at this intersection I am getting point O. So here what has happened, that after bending, A has been shifted to A dash, B has been shifted to B dash, similarly C dash and D dash. Next, after this we have layer EF, so that layer EF will be E dash F dash, that is the neutral layer, and here we have the neutral axis. Similarly, the layer GH, it will also shift, so we have G dash and H dash, this is the layer. Now the distance from the neutral axis to the layer G dash H dash, that was Y we have taken. Next, I'll assume that from point O up to the neutral layer, that is layer E dash F dash, this radius I am going to assume it as capital R. So now I'll say that for this diagram, let the beam may bend as shown in above figure. So now after this I'll say that let the beam may bend as shown in figure. Here I'll say that capital R is equal to radius of curvature of layer E dash F dash, that is the layer here E dash F dash, its radius with respect to the center is capital R. Next, after this I'll say that Y, which is the distance from neutral axis up to layer G dash H dash. Next, I'll say that the angle here, I'll take it as theta. So theta is angle subtended by arc at the center, that is theta. Now after giving the notations, the next thing would be, since we can see that previously this layer GH, it was straight, but after the load has been applied, that layer is bent. So the shape of this layer has changed. It means when the shape has changed, there is strain in that layer. So I'll say that therefore strain in layer GH due to bending. Now that strain will be denoted by E is equal to, and the formula of strain is change in length upon original length. So here the change in length is, it is G dash H dash, that is the final length, minus initial length was GH, also called as the original length. So here change in length is G dash H dash minus GH, which was the original length, divided by GH, that is the original length. Now, but I can say that, as it is clear from the diagram before bending, GH is equal to EF. So here I'll say that therefore E is equal to G dash H dash will remain as it is, GH is equal to EF, and here I'll mention, since GH is equal to EF. Now after this, reaching at this stage, I will call this strain equation as equation 1. Next, now since length of arc E dash F dash or EF is given by, now that length of arc is nothing but EF, or we can say E dash F dash, both are same because at the neutral axis the length of arc remains same before and after bending. So therefore it will become EF is equal to, now to calculate length of arc, since E dash F dash, here I am getting the radius of it as capital R, so capital R radius into theta, that will give me the length of arc here. So EF is equal to R into theta, that is the length of arc which I am getting. Next, this length of arc which I am getting, it is for EF. Now similarly I will calculate the length of arc for G dash H dash. I want to know the length of this arc, so I'll say that similarly length of arc G dash H dash is given by G dash H dash is equal to, now for this layer the distance or the radius of this layer is capital R plus Y into theta, so capital R plus Y into theta. So hence here G dash H dash will be R into theta plus Y into theta. Now after reaching at this stage, therefore I'll say that in equation number 1, G dash H dash minus EF, that represents the change in length, so I'll say that therefore change in length, which is denoted as delta L, is equal to G dash H dash minus EF, so it is equal to R theta plus Y theta minus EF was again r theta. So r theta. Next, from this plus r theta minus r theta, it gets cancelled out. So we have, therefore, deflection delta L is equal to y into theta. Now, after reaching here, the next thing would be, here I'll put the value of change in length and original length in equation 1. So therefore, put all values in equation number 1. So in equation 1 we have strain small e is equal to, now g dash h dash minus ef, that is change in length. Change in length is delta L, we have found out it is y theta, upon the original length, which is ef, it was r theta. So from this, numerator and denominator, theta will get cancelled out. So therefore we have strain is equal to y upon r. But I can say that from Hooke's law, as we know that in Hooke's law stress is directly proportional to strain. When we remove the proportionality sign, we have a constant which is called as Young's modulus. So strain will be stress upon Young's modulus. So I'll use this relation, and therefore instead of small e, I'll write down stress upon Young's modulus is equal to y upon r. Next, I'll shift the terms. So therefore sigma, I'll keep it as it is. Y, I will shift it in the denominator here. E will go into the numerator divided by r, keeping this as the second equation. Now, after this, I'll say that therefore from equation number 2, bending stress acting on the layer is given by, I'll keep sigma on one side because this sigma is nothing but sigma suffix b, bending stress, and I'll shift y onto the other side, so it becomes E by R into y. So now here I am getting this bending stress equation. I'll call it as equation number 3. Now as we can see from equation 3, capital E and capital R, that is Young's modulus and the radius of curvature, which is at the neutral axis, this capital R, it is a constant. So I'll say that from equation number 3, we see that Young's modulus, capital E, and radius of curvature, capital R, are constants. So therefore sigma b is directly proportional to y. Sigma b becomes directly proportional to y. Now after reaching at this stage, I'll say that consider the cross section of the beam as rectangular, and in that consider an elemental strip having area dA located at distance small y from neutral axis as shown in figure. So now here I am going to consider the cross section of the beam as a rectangle Here we have the neutral axis. In that I am considering a small area or a small strip. Now this small strip has area dA and it is located at distance y from the neutral axis. Now the next thing would be, I'll calculate how much is the force acting on this elemental strip because of bending. So therefore force acting on the elemental strip because of bending. Now that force is nothing but small amount of force dF because it is acting on small area dA, and that force will be equal to bending stress into area. Here I can write down, since stress is equal to force upon area, so therefore force is equal to stress into area. So I have used a similar concept here, that the force acting on the elemental strip is small dF and that is equal to bending stress into area. Now here we have found out the bending stress in equation number 3. It was capital E by R into y into dA. Next, now after getting this force, I will take the moment of this force, that is here I am getting the force which is acting on this elemental strip, which is dF. Next I'll take the moment of this force about the neutral axis. So therefore taking moment of force about neutral axis, so we have that moment as small dm, that is equal to small amount of force into distance y, and here df is equal to E by R into y into dA into y. Here I have put the value of df. So next dm will be E upon R, y into y will become y square dA. Now this much is the value of the moment which is acting for that elemental strip, the moment which I have taken for that small strip. Now if I consider the entire beam, then the moment will be, so therefore total moment of the beam about neutral axis. Now for that total moment, here I will have to integrate this equation. So here integration of dm will become capital M. Next, after this, here E by R, I'll keep it as it is because it is a constant. Now one thing interesting here is, this is area and distance square. So area into distance square, that is called as the second moment of area, because distance is y and when I am taking the distance twice, it becomes y square, and y square into area, that is called as the second moment of area, and second moment of area is nothing but I, which is the moment of inertia. So I'll write down where I is equal to second moment of area, or it is called as moment of inertia about the neutral axis. So here I have replaced integral y square dA by I, which is the second moment of area. Next, here also I'll shift the terms. So m, this I will be shifted in the denominator. On the right hand side we have E upon R, keeping this as equation number 4. So here as we can see, from equation number 2 we were having sigma y upon sigma upon y is equal to E by r, and this sigma is nothing but sigma suffix b, that is bending stress. So I'll say that from equation number second and fourth, sigma b upon y is equal to, here it is E by r, and similarly in equation 4 we have E by r, so E by r is also equal to m upon I. So from both the equations I am getting this form. Next I'll write it as, therefore m upon I is equal to sigma b upon y is equal to E by r. I have written it in this form, and this equation which I am getting here, I will keep this as equation number 5, and this is nothing but the flexural equation. So therefore from equation number 5 we are getting the flexural formula, or it is also called as bending formula or bending equation. So now here in equation 5 we are getting the bending formula, or it is also called as the flexural formula, and I'll define all the terms, where capital M is called as bending moment, and since it is bending moment, the unit is either it can be Newton mm, or it can be Newton meter, it can be kilonewton meter, and so on, because it is force into distance. Next I, it is called as second moment of area, its unit is either mm square, mm raised to 4, centimeter raised to 4, or it can be meter raised to 4. Then we have sigma b, which is called as bending stress, and the unit is Newton per mm square, or it can be kilonewton per mm square, or kilonewton per meter square, so on. Next y is the distance of layer in which bending is considered from neutral axis. So this is distance, so it can be in mm, it can be in centimeter or meter. So y is the distance of the layer in which bending is considered. Next capital E, it is called as Young's modulus or modulus of elasticity for the beam material, and Young's modulus unit is Newton per mm square. At last we have capital R, which is called as radius of curvature, and that radius of curvature of beam, it is, since radius, so in terms of mm, centimeter or meter, and that radius of curvature of the beam, it will be in the terms of mm, centimeter or meter, and it is the arc which is formed when the beam gets bent. So here in this video we have seen what is the flexural formula and how it is derived.